Very good afternoon to everyone. Today we are having 56th Professor Ananthakrishnan Colloquium by Dr. Vivek Mugundhan. I met Dr. Vivek just a month ago in KAUST. He is presently doing a postdoc in King Abdullah University for Science and Technology in Saudi Arabia in Mechanical Engineering Department. He did his PhD from KAUST. Before that, he did his master's in Thermal and Fluid Sciences from IIT Bombay. And he has done his bachelor's from Amrita University. When I went to Dr. Vivek's lab in KAUST, I could see very nice PIV measurements that their group was doing. And I had extended discussions with him also. And then I felt that when we were discussing, he said that he's going to come to India in the month of March. So then I asked him why, if he could come down to IITM and give a talk. So here is Vivek today. So Vivek,
thank you so
it's much. Over to you.
Thank you so much.
So you have got, how much is the time for this? Typically 30 minutes? Let's say 30 minutes. Yeah. Okay, over to you.
Good afternoon to all. First of all, I thank.
Voice is very.
Good afternoon. Good afternoon to all. Thanks for coming for this talk. I thank you all for inviting me for this seminar. A special thanks to Dr. Dixit, who was kind enough to invite me for this seminar. The talk today is about high-speed volumetric measurements of turbulent flow through a contraction using Lagrangian particle tracking velocimetry. This is not just my work. So many people involved in this work. I would like to acknowledge them. First, to start with, my advisor, who is my PhD as well as my postdoc advisor, Professor Siggy Thoroddsen, who has given me the facility and advice all through these years. And two other people who are no more with us, my PhD co-advisor, Professor Ravi Samtane, who has been a great support all through these years, who passed away 2 years back. And my other colleague, Dr. Pugalendi Ramakrishnan, who was from ISRO and was doing PhD in KAUST. Unfortunately, he passed away. He was very instrumental in bringing me into this area of research. And I would like to thank Dr. Abdullah, who shared some of his results. He just defended his PhD last month when Dr. Dixit was there. And Dr. Kenneth and Dr. Nathan, who I worked with the experimentation of tomographic PIV. So this work was carried out at KAUST. This is the outline of my presentation. So I'll introduce what the talk is about and the flow configuration that we have. A brief literature survey, then talk a bit of experimental setup, the methodology that we adopt, and share some important results based on 3 sets of experiments that we did, and finally summarize what our findings are. We all know turbulent flows is encountered every day. And the basic nature of turbulent flows are that it is unsteady, 3-dimensional, and fluctuating in nature, has a wide range of applications in everyday life. To start with, maybe it's very important in mixing, determining the combustion efficiency, be it transport of heat and momentum in atmospheric or oceans, or the mechanism of heat transfer in heat exchange devices. These are the positive impacts of turbulence, but there are negative impacts like the pressure drop in engineering devices or any safety concerns that we encounter. So it is important we understand turbulence from the point of view, not just for understanding, but to predict better as well as develop control strategies. Just to give an introduction, just to give an overview of turbulence, the main challenge with turbulence is that the existence of a range of length scales and time scales, which makes the measurements very challenging. So as you all know, the conventional approach has been statistical, as people have already seen. But after the seminal works of people like Klein and others, Brown and Roshko, or Head and Bandyopadhyay, there's been significant interest in visualizing these large-scale coherent structures. So Klein and others were the first to identify these streaks, which you see on the top left, which is very close to the wall-bounded flows. And Brown and Roshko has been a very famous work, and it was cited by JFM for a very, very long time. I mean, highly cited paper in JFM for a very long time. They observed the mixing layer in a helium-neon flow configuration where they saw these circular vertical structures, and they had very significant shapes depending on the Reynolds number. And Head and Bandyopadhyay were the ones who observed, may not be the first time, but very extensively observed these hairpin and horseshoe vortices which emanate from the wall-bounded flows. So the interest towards large-scale structure has been significant and may not be so plausible from the experimental point of view, but has been studied extensively using by the modeling people in DNS and LES. But it is believed that large-scale coherent structure study, though may be unconventional, can give better understanding into the dynamics of turbulence. So conventionally, it's been the single and multi-point measurements using hot wires, which loses the three-dimensionality of the flow. But with today's imaging techniques and the speed of computing and the faster algorithms that are being developed, I think the volumetric measurements can contribute a lot to large-scale structure studies. So that's the whole purpose of this presentation. So the geometry that we have been studying for a long time is a contraction. It's just a fluid duct which is reducing cross-sectional area, which we encounter in various engineering applications, be it nozzles, in thrusters, or just to increase velocity. And in the turbulence community, it is a flow conditioner in wind tunnels which enhances isotropy. Weak contractions are used to increase the isotropy of flow. But in our case, the choice of geometry was to get prominent coherent structures. There's an existing theory for it. And to start with, for better optical access, we were starting with this experiment. So we chose a 2D contraction. So what I mean by 2D contraction is what is shown on the right-hand side. The contraction is only in the y direction. X is the streamwise direction. Contraction is in the y direction. And in the z direction, the front and back surfaces are just flat to give better optical access. So the theory is that if you have a vortex tube, which is having an angular velocity or a vorticity of omega-1, under the straining action gets stretched and becomes longer filaments as it moves out of the contraction. So they become very prominent and we can observe and measure these quantities. That was our aim. Just to give a perspective, the earliest theory is available from Prandtl 1933, who gave this theory for axisymmetric contraction. The pictorial representation is picked from Uberoi, one of the first experimentalist who tried to verify this Prandtl theory. So Prandtl actually visualized turbulence consisting of discrete vortex filaments. So the control parameters that we have here is the contraction ratio capital C, which is area ratio inlet to exit. And the other one is the local contraction ratio, which is area at any given X location divided by the exit area. So the Prandtl's visualization was that if you have a vortex filament, something like this, which is aligned with the mean flow direction, that is the X direction in this case, gets stretched because of the mean acceleration that you see. And the acceleration by volume conservation would end up getting smaller area, longer filaments with smaller area. And by Kelvin circulation theorem, you would end up getting faster angular velocity from these filaments. On the other hand, the filaments that are perpendicular to the mean flow will get compressed, increasing the area so that the angular velocities should come down. So this was a theory which he built for an axisymmetric contraction. So we end up getting this major observation saying that the streamwise omega should amplify as proportional to the contraction ratio, whereas the transverse one decays as 1 over square root of C. How does this translate to mean fluctuation? I mean, velocity fluctuations is the streamwise velocity should decay as 1 over C and transverse should grow as square root of C. This has been there for a lot of time. And there have been people starting from Taylor, Ribner and Tucker, and even in the 70s, Professor K.R. Srinivasan and Narasimha have done rapid distortion theory to get predictions of this model. But there has not been any experimental investigations on the coherent structures. So just to get a perspective, what are the literature available? There have been an n number of experiments. I would like to highlight the main ones. Uberay was the first one to do experiments verifying the Prandtl's theory, but he said the theory is only holding good for small contraction ratios, which is less than 4. Beyond that, the whole theory does not hold good. This was seen by Hussain and Ramji, Najib, Tana-Teacher, and Warhoft, and so on and later on. So all these experiments that we see were all with hot wire measurements, where they were only measuring the velocity fluctuations. They couldn't even go to the vorticity for that matter. But eventually, this important work by Ayyalu Somejila and Warhoft from Cornell, they actually did the study for a wide range of Reynolds number. So here in this kind of turbulence, the characteristic Reynolds number is the Taylor Reynolds number, which is R lambda, ranging from 40 to 470. And they still kind of verified the Prandtl's theory and said that's a weak contraction, verified the Prandtl's theory. But all the understanding was challenged by Ertung and Durst, who said that the Prandtl theory actually holds good for a wide range of contraction ratio, and all these observations which have been made were primarily due to noise in the measurements. So they argued it, which was very challenging, but it still remains to be proven whether Prandtl theory holds good for a range of contraction ratios. Those were the available 3D or axisymmetric contractions, but still there have been studies on 2D contraction like what we have done. One was started by my professor Thordarson Vanata, 1995. They've looked at passive passive fields using temperature as the scalar, passive scalar, and Brown and others have looked at using LDV. And even recently in 2006, Chen, Menevu, and Katz had looked at the same 2D contraction using planar PIV. So what we see is conventionally contraction has been studied with either hot wire measurements or to the maximum planar PIV, but this picturization of core and vertical structures have not gained much of a focus. And DNS people also don't talk about it because simulating a contraction is not that easy. So coming to the experimental setup, how did we achieve this experimentation? For that, we used a constant head vertical water tunnel that was built in KAUST. So we have an overhead tank where water from an overhead tank flows through a set of perforated plates and honeycomb, which we all do to bring down any large-scale fluctuation, large-scale structures which are inherent in the flow. And then it is allowed to enter into a grid, which is specifically called an active grid. What do we mean by active grid? We'll come to it in some time. The purpose of this grid is that it injects a tailored turbulence. You get repetitive turbulence being injected into the flow, and then we see how the turbulence behaves through a contraction. So the contraction is a certain downstream distance from the active grid, and then the water goes back into the supply tank. So all these pumps and valves is just to maintain a constant water level. Gravity driven just to minimize any incoming turbulence, and all the turbulence that was generated is from the active grid. So this is the setup that we have. You can see some of those important components. The supply tank, you can see the overhead on the top. The active grid has been secured by those waterproof sheets. And you can see these high-speed cameras, 2 of them kept on one side of the contraction, and 2 are seen from the other side because of the constraint of space. An important point is the whole setup here, because the measurement that we do is a volumetric measurement, is very sensitive to any disturbances. So it has to be made sturdy. So the whole setup has been made sturdy by using these rigid X95 structures. Some pictures of the flow conditioners. We have the perforated plates and the honeycomb to kill any large-scale turbulence. The first contraction that we studied is a 2D contraction, as I mentioned. So this is based on a 5th-order polynomial picked from that reference, which was cut in an acrylic block, and it was sandwiched between 2 glass plates. So these glass plates were given so that you get good optical access. So that's the contraction that we are studying, and a better view of the contraction from the front is this. So you can see from the front glass, you can see 2 of the cameras on the opposite side. The start and end of contraction is seen. There is a development distance of about 150 mm before and after the contraction. That was given. And what you see there is a black calibration plate. So this is an important step in any imaging study, because you don't know what is the physical coordinate that you're measuring. So In order to relate the physical coordinate into your camera coordinates, we have to use a calibration plate. So that's calibration is placed in the region of interest, which we try to measure. So now coming to an active grid has been there for a long time. It's a technique which is used to generate high Reynolds number quasi-homogeneous isotropic turbulence. It was first designed by Makita, but most of the designs that you see in wind tunnels is by Midlarsky and Warhoff, who have contributed significantly in this field. And it is seen that the Taylor Reynolds number as high as 1,000 can be achieved, which can be very relevant in atmospheric flows as well. So you can achieve very large fluctuations using active grid, which is not possible with just a passive grid. So that's what we have. To give an idea of what the active grid that we use, was built and designed in our lab. So we have a biplanar grid with 5x5 shafts, and each shaft is connected to these flaps, which has through holes through them, and each shaft is connected to a stepper motor, so they can independently be controlled. The speed and the rotation can be controlled, and so you can inject a very repeatable turbulence into the flow. The mesh size, which is characteristic of such flows, is about 30 mm. So the control parameter here is, one is the rotational speed, and the other one is how do you rotate these shafts. So based on the rotation modes, we initially tested with 4 synchronous modes and 1 random mode. What I mean by synchronous mode is these shafts are rotating in sync with each other, whereas the random mode is where the rotation is going to be in a random fashion. So the rotation in one direction for a particular period of time, which is called the cruise time, and then it changes direction and so on and so forth. So it has its own advantages. So we did rotation speed ranging from 3 to 4 revolutions per second, and the maximum inlet velocity that we could get was 0.3, because we were limited by the gravity flow. So we could get is 0.3 meter per second. So just to give you an overview, the first mode, which is this, sorry about the speed. So that's the first active grid mode, where you say that the shafts are rotating in sync with each other. If you closely notice that the alternate shafts are going to be rotating in the opposite direction. Sorry about the speed, probably. Whereas in the in the random fashion, I don't think things are not very clear, but at least you can make out that certain parts of the grid is open, certain parts of it is closed. So the direction of rotation is very randomized, and so you get a different kind of turbulence being injected. Now, the main part is about the experimental methodology. So just a brief overview, again, kind of measurements which have been used in turbulence. As we all know, that the classic way of measuring turbulence is using hot wire anemometry, which is an intrusive measurement, at least after the probe. And it's been widely used. It has helped to build a lot of theory in this field, but the spatial resolution is limited in the transverse direction. Laser Doppler is available. It's a non-intrusive technique, but the problem is it's not so widely used. I think probably is because of the way it is being set up. It's very difficult. But imaging-based technique is started with PIV by Adrian. What we do here is we illuminate a flow domain seeded in with particles, and then we measure the velocity. So in a PIV, so we get in a plane, which is a 2D plane, we get 2 components of velocity. So you get U and V velocity. That's PIV. An advancement of that by Prasad Adrian is the stereo PIV, where you illuminate not just a sheet, but you illuminate a thick sheet. So you get in a 2D plane, you get also the out of plane velocity. So it's like 2D, 3C kind of a measurement. And then in 2006 is where the tomographic PIV was brought in, and then it's become quite popular. The imaging technique would require at least 3 cameras. Many times it's going to be 4 cameras. So you illuminate a laser, you illuminate a volume in the flow domain. So you get in a 3-dimensional domain, you get all the 3 components of velocity. So 3D, 3C kind of a measurement. If you have a high-speed camera, you can get it time resolved. So you get 4D, 3C kind of a measure. And the advancement of tomographic PIV is what is scanning tomo PIV, which was implemented in our group by Casey Sakagibara and my advisor, Professor Throdson, where they used a volume and they scanned over over a larger depth. So the advantage is you get a larger 3D domain of velocities. They were able to measure a complete turbulent jet using this measurement technique. And then we have this Lagrangian particle tracking velocimetry. It's very similar to TOMO PIV, just that the algorithm that is used is different. So it's very particle tracking based algorithm. So you can also get 4D, 3C kind of a measurement, but the algorithms are very effective that the calculations are faster. That's Lagrangian particle tracking velocity, which is what we did. And then we have, this is again a development in our group in collaboration with another group called the single camera 3D PTV, where you use one camera and get a three-dimensional velocity field. So this was by Aguirre, Pablo, and others. So what we implemented is the Lagrangian particle tracking velocimetry that we'll see. So just to introduce what tomographic PIV is all about. So what we do here is you take a laser beam, use a set of cylindrical lenses and illuminate the flow domain. The flow has to be seeded with some neutrally buoyant particles. So you can see that the laser beam is made into a laser volume, illuminating the flow with particles inside. And the particles are going to be seen by at least 3 cameras, in this case 4 cameras, and they're all going to be focused in a common region of interest, which is denoted by that rectangle. So at a given time, you'll get 4 set of particle images from 4 cameras. So at time t, you get 4 images. At t plus delta t, you get another set of 4 images. So what the algorithm is need to be done is using these 4 images, you reconstruct the 3D position of the particles. So using 4 images at t, you get the 3D distribution at time t. Similarly, at t plus delta t, the another distribution, and then you use the cross correlation technique to get the velocities. This is what has been done in tomographic PIV, where the velocity computation is primarily by cross correlation. So what improvement happened with Lagrangian particle tracking velocimetry is the way these velocities are computed. So in the correlation-based TOMO PIV, which is the classical approach, some of the aspects are, it has been previously employed, it is an older method, and the advantage is it can handle very high concentration of particle. You can seed the flow to very large concentrations and get the velocities out of it. But the disadvantages is, because of inaccurate reconstruction, you can end up getting unreal particles, which in the literature we call it ghost particles. And because it uses cross correlation, there's certain amount of spatial averaging. And also the 3D reconstruction algorithm is very demanding in terms of computation, which makes this technique very costly. On the other hand, the LPT, which is what we are focusing on, uses an algorithm called Shake the Box, which was introduced in 2016 by Shans and others. So basically, it's a particle tracking algorithm. So you're going to track every particle in the domain, but the algorithm was very efficient in a way that it could handle concentration as high as TOMO PIV. That is what made it very attractive. And because it is a Lagrangian technique, so the velocity of particle is more accurate, and you can also get the particle acceleration. So that's another feature that we have. And we also notice we have done both the computation, and we see that Shake the Box is much faster, at least by 4 to 5 times compared to the correlation-based TOMO PIV. So this is how Shake the Box processing is done. So basically, what you do is you get the particle positions for the first few time steps, which is denoted in the yellow color, which is using a kind of a 3D reconstruction technique. So you know the particle history for a first few time step to start with, and using the particle path, you fit it and extrapolate it to get the new particle position, which is like indicated by the blue dots. Right? But definitely the extrapolated points may not be the real position of the particles. So what you do is you try to shift the particles in X and Y and Z directions. So basically, you're shaking the particle positions, hence the name Shake the Box. And once you shake it through a certain distance, you reproject it on the cameras and compare it with the actual images. So you get a residue between the actual images and the projected images, and then you correct it to minimize this residue. So this is how the algorithm works. So we didn't write the algorithm, we use LaVision's Davis software, which does this calculations for us. Okay, coming back to the illumination, the idea. So we have the basically a high-speed ND-YLF double pulse laser through a set of line mirrors. We focus it onto a cylindrical lens. So we expand the laser beam into a laser volume. something like this. You can see the laser being taken through a laser optics, making it into a volume. And then the laser volume is cut down using an aperture plate. So the laser volume is not going to be regular. You will have uneven edges. So they're going to be cut, forming a regular cross section on the test section. And once you have that, in the picture, you can see that the laser is actually illuminating the calibration plate. This was done before the experimentation. And then the illuminated volume is seen such that cameras C1 and C2 are seeing from one side and C3 and C4 are seeing from the other side. So we have 4 cameras capturing these images. So the better picture can be seen here, where the particles, the flow is seeded with particle and the cameras are capturing the particle images. The 2 sets of cameras have been used. In the very beginning, we used the Lagrangian Imager Pro 4 megapixel camera at 1279 frames per second. And then we went on to use a better camera, which is Phantom V2640, 4 megapixel at 6600 FPS. And the very important step, at least to give an idea, because it's a non-intrusive technique, you need to establish a mapping relation between the 3-dimensional coordinates to your sensor coordinates. So this process is called calibration. So what we do is we have a calibration plate with specified number of dots. The dot sizes are known. So the software is able to pick the coordinates and generate a relation between the actual physical coordinates and the sensor coordinates. It's very important. Otherwise, the measurement does not have any meaning. So for that, we use a calibration plate from Lagrangian. And in tomography, you have another aspect called the volume self-calibration. As I had highlighted before, the experiment is very sensitive to measurements. So once you've calibrated, if you disturb the system and the calibration is gone, then the measurements are all waste. You cannot take any data out of it. So to account for it, what we have is called the volume self-calibration, where the particles are used to correct the calibration. If in case there is a misalignment, not a very large misalignment, but a small misalignment in the setup, which is possible because you're going to take experiments over the entire day, then these things can happen. So this volume self-calibration will help to correct the calibration. And to give in details of the particles, we use fluorescent particles so that we get good signal to noise ratio. And the density was slightly higher than the density of water, giving us a Stokes number of 2 × 10⁻⁴. So now how do we get the velocity? So steps that we get is, we'll get particle image something like this. So all the particles which are fluorescing will appear bright in your camera. So at a given time, we'll get 4 images. At time t, we'll get 4 of these because we are using 4 cameras. And then we put it through a set of processing. Background is subtracted and the intensities are normalized to get the processed images. And using the processed images, we can actually get the particle positions in 3D, which is the particles which can be tracked in time as well. So the particle is calculated. And once we have the particle path, you know the velocity. And using these Lagrangian velocities, you can always map it to a regular Eulerian grid. That is when you can do an analysis. So velocities that we get are Lagrangian first, but then you map it to a Eulerian space. So after that, you can do whatever analysis that you would like to do. Here, you're just showing the contours of mean velocity with the streamlines of the flow, which is only possible in a simulation environment. But these are measurements that directly come from the experiment. And the main feature of this, the advantage of these measurements is visualization of the coherent structure. So what we are doing here is we are calculating, or we are showing the isosurfaces of vorticity magnitude, which kind of represents the coherent structures which are inherent in that particular flow. And all our study was on these coherent structures. Just to give a perspective, the nomenclature that we use, capital U is instantaneous and small u is fluctuation. Similarly, capital omega is instantaneous vorticity and small omega is fluctuation. Here comes the first set of experiments. So the first set of experiments we did with the aim of looking at evolution of turbulence. First time we are doing measurements with Tomo PIV in this configuration. And we wanted to look at coherent structures through a 2D contraction. So the measurements were done at 3 different locations, P1, P2, and P3. The measurements cannot be done on the same day, but they're done at different days with different alignments and different camera setups. So we used the Lagrangian camera, and acquisition speed was at 1000 and 1300 frames per second. These cameras typically have a total memory of about 100 gigabytes of data. So every data realization will generate a particle image of about 100 gigabytes. So to characterize turbulence, we calculate all those important turbulence parameters, the kinetic energy dissipation, the length scales, the Reynolds number, and the Kolmogorov scale. And I would like to highlight the important Taylor-Reynolds number, RE lambda, for all the four synchronous mode and the random mode. So what we noticed is, if you see sync mode 1 or the S1 mode gave us an R lambda of 280, the random mode gave us about 290. The other things were all smaller than that, right? So because these modes were giving us higher level of turbulence, we restricted our analysis, most of our analysis to these modes, which is the base mode, which we call the base mode and the random mode. So this is the mean velocity. So we are showing the mean velocity. Most of the statistics that we did was along the center line of the channel. So you can see that the velocity is accelerating. The mean velocity is accelerated to 2.5 times the inlet velocity. That's because of the contraction ratio being 2.5. The strain rate variation, because of a smooth profile that we have, it increases and then decreases. To judge the quality of the flow, we looked at the transverse profile before the contraction inlet is. So you can see in the base mode, you see kind of a sinusoidal profile. That is because of the signature of the grid coming into the flow. Whereas you go to a random mode, you get a more uniform profile. Because of the randomness of the grid rotation, we could get a more transversely homogeneous flow. So of all the modes that we compute, mode S1 and random mode gave us high levels of Reynolds number, and random mode specifically gave us a more homogeneous flow. And so we picked most of our analysis with these modes. This comes our first verification that the RMS velocity U is streamwise and V is transverse. The first part before the first black line is before the contraction. X is equal to 0 corresponds to start of contraction. So U decays continuously, and this decays, if you go back, I mean, if you recall what we talked about, the Prandtl theory is decaying is 1 over C, and it behaved kind of 1 over C after the contraction. But the transverse component has to grow a square root of C, but we see a very small increase in the transverse RMS, but they were not as strong as what Prandtl would predict. That probably is because ours is not an axisymmetric contraction. And also these measurements were not done at the same time. There was always measurements done on different days, certain misalignments and so on. This is what I would like to emphasize, is this measurement is able to predict the RMS vorticity. So you cannot do this vorticity calculation with a hot wire. Maybe you'll have to do many times with multiple probes. But here, because of the fact that we get 3D velocity, so the vorticity information is available to us. So omega x growing and omega y decaying was able to be predicted. We were able to predict omega x growing and omega y decaying, which Prandtl had predicted. And what is interesting to see is omega z, which is the vorticity in the z direction, which is normal. Which is not seeing the contraction, gets unaffected. It remains unaffected by the contraction because that component of vorticity does not see the contraction. So the results coming out of these measurement techniques were making meaning. But here comes our focus, looking at the coherent vertical structures. So what coherent vertical structures, as Hussein, one of the leaders in this area, defines, is a connected turbulent fluid mass with instantaneously phase correlated vorticity over its spatial extent. So how do I visualize it? There are multiple criteria. So the simplest one is just looking at vorticity or the vorticity magnitude itself, or you can look at properties of the velocity gradient tensor like the delta, the lambda 2 or the q2. But all those things which you relate to the velocity gradient tensor would involve operations on velocity. Velocity itself is accurate to some level, but the gradients would be a little bit less accurate. So we wanted to be simple, so we picked the vorticity magnitude to visualize the coherent structures. So P1, at the beginning of the contraction, what we noticed is by visualizing isosurfaces of vorticity magnitude, these are not numerical simulations, but experimental measurements. The structures were kind of broken down, smaller in size and randomly distributed. But as you move to position P2, because of the strain applied, you can see certain structures have been extended, have been elongated, and you can see structures being guided towards the center of the flow. So the dynamics is coming out from these measurements. So now at position P3, you can see very long filaments which are very much aligned with the mean flow as expected or as postulated by Prandtl's theory. So you can see these fine structures, long structures, which have become very much aligned with the mean flow, like the one which is highlighted in the system. So this is something which came out of our measurement. This is not going to be at certain instants only. When we measure it across, we have done this across 5 realizations of about maybe 5 terabytes of data, or sorry, 500 gig of data probably, and we still see many of these structures existing. So we wanted to quantify it. So we looked at certain PDFs and so on. So there are 2 kinds of PDFs. One is the point-based statistics that we looked at, the PDF vorticity vector, and the structure-based PDF. So what we mean by point-based vector is we are looking at the probability density function of omega with respect to the vertical direction. Minus x is opposite to the mean flow because in our case the flow is downward. So minus x is opposite to it. So we present PDF of cosine of theta. And the same way we look at not only the vorticity vector, which is a point vector, we also look at the orientation of the structure. So there are 2 kinds of things. One is point statistic and the other one is structure statistics, and see how it behaves. Now the question is, why are we presenting probability of theta, I mean cosine theta and not theta? So this has been there in the literature, but people don't really explain a lot. So we struggled a bit to understand this. So the reason is, like, if you take any given theta, the probability of having theta in a hemisphere is given by that strip area. So the probability of having theta is going to be the strip area divided by 2 pi r square. So there is inherent bias. When theta is equal to 0 corresponding to the north pole, the probability is less because of a small area which is subtended there. But as theta increases to 90 degrees, the strip area is more. So at the equator, you have a higher probability. At the pole, you have a lower probability. So you need to correct the PDF. If you take a calculation of, I mean, you compute a PDF for theta, but if you do it for cosine theta, this automatically takes care of it because cos 0 is 1 and cos 90 is 0. So that's the reason that people do it. So when you have a vector, red vector, which is at 90 degree with respect to the reference vector, then the cosine theta is 0. When is it, let's say 60, it's 0.5. When it is aligned with the reference vector, it's going to be 1. So when we say cos theta is 1, means it's perfectly aligned. So when you have a PDF something like this, you have all several vectors, vorticity vectors, which have been computed. And when you say that it is peaking at 1, which means most of these vectors are aligning with the reference direction. That's what it means. So this is what we have been seeing. So what we did, we calculated PDF of vorticity vector at 4 different locations. One is before the contraction, the red one, which is minus 90. And the other one is at 190 after the contraction. So when it is at before the contraction, the distribution is almost flat, which means all these vorticity vectors were random, uniformly distributed. But when you go to 190 mm, it becomes biased, with most of them aligning with the flow. So this is, I will skip this result. Now, looking at coherent structures, how do they behave? So we have seen these repetitive coherent structures, but how are they aligning with the x direction or the negative x direction? For that, we need to characterize these structures. So for that, we use 2 thresholds. The algorithm that we used is based on the vorticity magnitude, and the other one is the volume. So whichever structure which is greater than vorticity threshold of vorticity magnitude and volume, we choose them as a structure. And each structure is approximated by an equivalent ellipsoid. And we look at the centroid of that ellipsoid and the axis of that ellipsoid. So this is what we have. So those pink structures that you see are structures identified by the code which was developed. The center and the line is going to be the centroid and the line of the ellipsoid, which has the same moment of inertia as the pink structure that we see. So at position P3, maybe at position P1, you can see the structure orientation is in all possible directions. This is only one instantaneous. But then as you go to P3, which is at the exit of the contraction, you see most of them are aligned with the x direction. So this bias that we saw with vorticity was true with the structures as well. So we ran this through a PDF. So it was like we had something like maybe 100,000 structures over the entire time period, and we built the PDF. So at position P1, you see the distribution is more flat, uniformly distributed, but at position P3, they become very biased, having a peak close to the exit. So this is the bias, I mean the orientation, and we saw the same profile P1, P2, and P3. The distribution changes from a more uniform profile to a biased profile, and this is true for both base mode as well as the random mode. So this was done first thing, and then for the future experiment, this is again concerns from the review when we submitted our paper, saying that they were asking about how good the quality of the flow is. So what we had to do is the upstream distance before the contraction, which was about 250 mm, was increased to almost half a meter. Now it's 478 mm, and we repeated the experiments again. And what we noticed is that without the extension, the RE lambda was 226, but with the extension, the Reynolds number has to decay. The fluctuations would decay, so it had to come down to 109. The mean profile, there was a more uniform profile as expected, but did not affect any of our results. So that came in hand, saying that any kind of inhomogeneity at the exit did not affect the structure behavior. The inlet conditions did not affect the conditions. So just to summarize the first experiment, so the conceptual picture of Prandtl was of stretching and alignment was verified because of the fact of that we are using volumetric measurements. We were able to achieve RE lambda of 250, which is significant. And any independent, the statistics that we presented were all independent of any inhomogeneities that we had. So most of the results, you can look at our paper, JFM paper, if you're interested. In the second set of experiment, we wanted to look at circulation. So for that, we had a 2D contraction, but this time we had a better camera, which is a 4 megapixel at 6600. So we focused on only two regions, position P1 in the beginning of the contraction and P2 at the exit of the contraction. Just to give an overview of what circulation basically is. Circulation is if you have a closed loop drawn in a fluid domain, then circulation over that area A is going to be the cyclic integral of u dot dl. And because omega is del cross u, Stokes theorem, you can say that this gamma A is going to be omega dot dA. So what is the advantage from a fluid dynamics point of view? You can calculate the features or characteristics of omega from gamma A without even calculating omega, because gamma can be calculated using velocities or calculating omega. So that's the advantage. So you don't have to get into vorticity to get information about vorticity. There's been significant interest about vorticity, about circulation, starting from Migdal, who gave the theoretical formulation, and Professor Srinivasan, who has been working on this for a very long time. Even till 2021, there has been significant results on circulation. Some experimental explorations by Srinivasan and others in wake of a cylinder, Zhao and others in Rayleigh-Benard convection, and Thorarts, my professor, had done with grid turbulence. So all these studies have been with 2D PIV, but we have a 3D PIV now. So the advantage was we were able to get circulation not only in one plane, but we were able to get circulation in 3 planes. So circulation as seen as a scalar, we were able to cast it as a vector. So we can calculate gamma x, gamma y, gamma z as 3 components of circulation and see how this behavior happens. So this is just some pictures of the mean velocity that you see. That you can see that as the flow is progressing through the contraction, the mean velocity is accelerating. That's because of the contraction. The acceleration is more uniform in the random mode compared to this base mode. The same is seen with the RMS vorticity as well. So when we looked at this circulation as a vector, we normalized it by, we calculated the PDF of relative strength, that is gamma x, gamma y, or gamma z, normalized by the amplitude, which is square root of gamma x square plus gamma y square plus gamma z square. So what we noticed is the red one, which corresponds to the streamwise circulation, had a very similar behavior as the structure itself. It had a biased behavior, whereas gamma y, which is the transverse direction, was peaking at 0. So this was very much in line with the results that we saw with our structures. So this was only possible again because of the 3D measurements. Some additional studies that we did saying that the PDF is going to become more Gaussian as you increase the loop size. This was also possible. So simultaneous circulation were calculated and we casted circulation as a vector and we saw similar observations as what we saw in our previous results. And very recently, my colleague Dr. Abdullah had done these experiments in a 3D contraction. So there, where we were doing contraction with 2.5:1, but here he has done experiments with C equal to 16. And these were done with the same V2640 cameras and an acquisition speed of 1300, but these cameras have a combined memory of about 1 terabyte. So one realization would give you 1 terabyte of information, and then you process it. The velocities that you generate is typically about 20 terabyte. So the information he generated is about, I don't know, a few terabytes raw data was generated, and he had to go through all these calculations. So in this setup, again, the measurements were done at P1, P2, and P3. 5 realizations were taken, only focusing on the random mode. And we calculated about 700,000 volumes and to identify these to run the statistics over these structures, which is typically about 100 terabytes of information. So this was all done using a high performance computing and storage with cloud and so on. This is again what we saw, the contraction. So at position P1, you can see that you see structures coming out of the grid, but when it reaches P3, you see very, very significant long structures. In the previous contraction, there was only, which was lesser than the measurement domain, but here you see structures which are even longer than the measurement domain of the of our experiment. So I don't know if this video would play, but to see the rainfall of structures. I think it's being shared. So this enabled us to do a lot of characterization of structures. One important characterization which has not been reported is how strong the structure, or the core of the structure, is going to be enhanced. So what we see is the core strength is enhancing almost by 4 times in this contraction ratio of 16. So I have not presented many of these results. So these large volumetric measurements with huge data sets has enabled us to characterize coherent structures, which has not been there available, to look at their orientation, like what I presented before, looking at their direction, preference of direction, the length, the diameter, and the core strength, which makes it. And this is one of the largest Lagrangian particle tracking data set that we have, particularly to this configuration. And you can look at this paper for more information. So just to give an overall summary, we use the Lagrangian particle tracking velocimetry to obtain high-speed volumetric velocity data in both 2D and 3D contractions. We were able to get turbulence of about 250 using active grid, and volumetric measurements have enabled us to look at all the 3 components of velocity together, which is only possible in DNS probably. And we've also looked at vorticity variation. From the fact that we have vorticity information, we are able to visualize coherent structures and try to characterize. And so this opens avenues for theoreticians to look closely how this can help in understanding dynamics in straining flows. Thank you very much.
Okay. Thank you, Dr. Vivek, for very nice talk, actually. Doing these things in the lab, we know how it is to be done, and it's very challenging to do these things. Anyway, so any questions for Vivek? Yeah.
Can you go back to that slide with different colors associated with different structures?
This one.
Yeah, so what does the color
the color is, these are isosurfaces of vorticity magnitude, but they're colored by the stream-wise vorticity. They basically represent the direction. So if you see at P3, the blue corresponds to one direction and red corresponds to another direction.
Right. What about the left one?
So they are all on the same scale. What happens is the vorticity magnitude, because of the stretching, amplifies.
Right.
So you get extreme vorticity magnitudes at the exit compared to the inlet.
Okay.
So it's more narrow. It's in the narrower region. It's like minus 0.5 to plus 0.5 in the beginning. It expands all the way to minus plus 2.
Okay.
Exit.
Thank you.
Any other questions? Okay, I will ask a question. So you said that these cameras are 4 megapixel cameras, right? So, and what is the physical size that you are looking
domain,
at? Domain size?
Yes, I think I don't have it. So this position P1 is actually full resolution, which is 4K, which should be around, you can say around 100 mm by 100 mm.
Okay.
With a thickness, typically all a measurement thickness is about 25 mm, not more.
Okay.
24 mm.
24 mm. Okay. So maybe then it's manageable because see, when you get the velocity information and you convert it into vorticity, you inherently have differentiation and associated errors, which you mentioned actually before. So how much that affects these estimates? Is there any
uncertainty
estimate that you have made for this uncertainty?
Yeah, we have some uncertainty calculated, but I cannot give you off. So I can always, we have done some uncertainty.
Yeah, because typically if people want to go for actual velocity field to be converted to vorticity, that's where you want to go for high resolution cameras rather than, the lower resolution will compromise on the gradients. But I liked your other way of getting an indirect estimate of vorticity from circulation. That's a very good idea. That I agree with. Any other questions? Oh, Madhu.
I just want to be curious that why the structures are mostly aligned vertically. Because the turbulent structures may come on the horizontal, like the 8-inch structure you have shown.
That's right. Exactly.
Made like vertical.
Exactly. That's the reason.
Flow.
Right. The contraction makes the alignment biased, which was initially randomized. So you can see structures here, at least in the previous experiment, the structures are very.
You could see some horizontal structures.
Right. There. But then the shape of the contraction makes them more aligned with the mean flow direction.
As it's rightly asked that the spatial structures, how much it will be. I want to extend that one to what you are told that you are taking 4 frames at a time.
Yes.
And you are taking the next set to the 4th frame.
Right.
The delta T.
Delta T we have gone is, ours is, I mean, it's not like the airflows that they do, but ours is typically we have gone up to, in this experiment, we have gone up to 5,000 frames per second. So which would give us like 1 millisecond. So 0.2 millisecond is the frame rate, the delta T.
Purely laboratory. So I am just connecting it to my real observation.
Right.
Okay.
Yeah, our velocities are small and then things. And we are using with water. So thank you so much.
No, I think one more place where some of these things could be relevant is, where pressure gradient plays a major role in some atmospheric phenomena, such as formations of cyclones and stuff like that, where you would be getting these stretching of vortices. But I don't know, people might not have already seen these sort of things. Or it might already be there. I don't know.
Stretching is very much there. There is no issue in that. But only thing your scale here is small. But this is very interesting. I was just wondering, why this lab KAUST is having? I mean, what is the purpose of having this lab in KAUST? What do they do finally?
So I'm associated with the high-speed imaging lab at KAUST. So our main objective, we study fundamental turbulence. This is
so that is the purpose.
Yeah, we study fundamental.
So it is good that KAUST supports fundamental science.
part of mechanical engineering.
Yeah, that's fine. I mean, nowadays it is very difficult to see that some institution is supporting a fundamental science. Now,
when the funding comes from industry, you cannot do fundamental
everybody
science.
is whether it is industry or government, everybody is looking towards application.
Yeah.
Nobody is there is no one. If C.V. Raman would have been present now, nobody would have supported his Raman effect experiment. Because they don't have foresight that this will be useful so much in even space, right? So it is good that KAUST is a.
Thank you so much.
Keep it up and all the best.
Thank you so much.
Is in terabytes.
Yeah.
Normal person can.
I think we were pushing to our limits, I think. Yeah. But the aim was like we wanted to run very good statistics. So the only way is to look for a longer time series, because to get a large set of data, I mean, a large number of structures only by looking it for a very long time. But definitely that is something which you have to face. The tomographic measurements consume, memory. I hope that in the near future there would be some ways by which.
Even if we do these LES, right? If you do a high resolution LES, you will get huge data. So this is very similar.
I think in terms of, there's significant amount of effort which is being done in improving these algorithms. So as I told you, like correlation based techniques were taking like 5 times more time compared to what we have in tracking. I think nowadays they're talking of AI based and things like that. So probably the time aspect can be improved a lot.
What you told is 1 terabyte when you to make the second level of analysis,
yes,
it became 20 terabyte.
Exactly, yeah. So the one realization in that camera is about, so each camera is about 250 gigabytes. So 4 cameras gives us 1 terabyte, which is 1 minute of information. It's just 1 minute of recording. Physical time is 1 minute. But then we take about a week or so of computations on the HPC to get these data, and then we process it.
So they actually have this HPC called Shaheen. And then on that HPC, these people run these PIV algorithms to process, because it's not possible to do it on even on a workstation.
Yeah, the advantage is like, I think the parallelization, I have not worked so much, but the advantage on HPC is you can fire all the instances together. So you bring down the time. Yes.
I have a layman's question. So if you run so many experiments of for turbulent theories, right, and you get big data, store them.
Yes.
And then you use all these your AI concepts. So will it possible that in future you don't need any lab? You only run in HPC with all your, all possible realization, and you just keep on, testing your hypothesis or see the manifestation. So you don't need any what is called fluid dynamics lab anymore. Yeah, I'm not both of you.
You want to answer it? Yeah.
No, I think, but the data set definitely is a good data set for training machine learning and all things like that. But I think the accuracy of all these machine learning depends on the good data sets that we need. I think we need good labs to generate these high quality data sets, I think.
So actually, there are people who are trying to do similar things for, breaking complex flows into imagining them to be made up of a combination of simpler flows, and create a database and then train things. And so it is there already. It's there. Yes, that process is already on. So if you want to simulate the flow of an airplane, okay, people are already doing, but they are not reporting that much success right now. That's a good thing for us.
I will sincerely pray that situation never comes. Your fluid dynamics like forever. Otherwise, we lose innovations and
Right. I think the DNS community puts up many of their data online, like the John Hopkins database and things like that.
Still, I think even with these computations going to these levels in recent times, but still the sort of Reynolds numbers that we are talking about are very limited. in the computations or even in the lab experiments. So if you go to atmosphere, those Reynolds numbers are not even anywhere close. So that is the ray of hope for us still.
So Reynolds is the hope.
Reynolds number is the hope.
Droplets with these vertices.
Ah.
Can you see that how they are interacting?
Yeah, actually, so that's a very good question. So I'll give you a background. So there is one Dr. Bipin Kumar who is not here right now. So he has a DNS code in which it's a two-phase, and then he tracks the cloud droplets. Okay, Lagrangian in Lagrangian way.
Okay.
So that is what I think he wants to.
In transition something.
Okay.
Like
I think we did see a work similar in the turbulence workshop also, where they were talking of some kind of tracer particles. They measure the tumbling rate and then the things like microplastics.
So people are doing these microplastics. See, in oceans and all that, these microplastics is a big issue. So they are putting microplastics in their experimental setup. Okay, and trying to see how
our application.
yeah, how these microplastics tumble and rotate and with the flow, and then how the interaction happens. A lot of effort is going in that direction also.
Maybe the vorticity and circulation is more accurate with those measurements, probably, if you can track these.
Yeah.
Yeah, sure. Thank you.
Okay. You have a question.
Sir, actually, when you have shown that vortex and computed that vorticity, and I would like to know that is there any signature at that scale, helicity of that?
Yeah, that's right. Helicity, I mean, we did start something, but we didn't go so much. I think we didn't progress so much. That's a good idea. We could look at helicity.
So you expect helicity at that scale?
I'm not sure.
Okay.
I haven't looked at it.
And second question is, you have computed the vorticity from that circulation, using that circulation integral?
No, I computed vorticity directly, but I said circulation is another way of understanding. So there are two ways of methods, right? One is vorticity directly, and the other statistics that we did was circulation.
Okay.
So there are two different studies we did. Yeah, definitely circulation is a little bit more accurate than.
Then you have mentioned about Q criterion and lambda.
Yeah, we have done some visualization with Q criteria and things like that, but
it is far more better what you have.
No, we didn't venture into it because Q criteria lambda 2 looks fine, great with simulations, I think, but with these measurements, I think they kind of trackability of these structures are not that great. When you go in time, basically, we feel that omega is much better compared to the other criteria. Yeah.
Okay.
Thank you.
Any other? Okay. If there are no questions, let's thank Dr. Vivek for good talk. Thank you. Can you check